Today we have two excellent lectures. The first one will be delivered by Professor Dietmar Stalke from the University of Göttingen. Professor Dietmar Stalke is one of the most known colleagues in our field. So probably for most of you, there is no need for extensive say introduction. However, there are many new people. So let me say a few words about Dietmar's career. He was graduated in chemistry and philosophy in 1983, and then in 1987 he got a PhD at the University of Göttingen under supervision of Professor Kringebiel. And in 1989, he started his postdoc with Professor Stach and Professor Paul Rightby at the chemistry department, University of Cambridge. And after some years there, he went to Erlanger and was having next postdoc with famous Professor Schleyer, who is really excellent who was an excellent theoretician. And in 1987, 1983, Dietmar got habilitation, which is specific for German and system and systems of neighboring countries, including Poland. In Germany, they have incredible system because at each university you have to do separate habilitation. So habilitation gives the right to teach. And that was done at the University of Göttingen, also with a very famous mentor who was Professor Sheldrick. Dietmar at first worked since 1996 to 2005 as a professor at the University of Würzburg. Then actually he picked a better position at the University of Göttingen, where he actually works up today. He is one of the most active people at this university. He used to be the Faculty of Chemistry between 2007 and 2009, Dean of Research between 2009 and 2011, Dean of Studies at the Faculty of Chemistry 2012-2015, and even the senator, one of the senators of the University of Göttingen since 2013. And as I know, there are only 12 senators there. I mean, I would love to have this situation at our university. We have 60 or 70, but it's not any better. Anyway, and since 2017 up to 2020, research at the Faculty of Chemistry, and again since 2019, Dean of Studies. So, as I remember, Dietmar was also a serious candidate to become director of the university. Dietmar got plenty of different achievements and honors. He's been distinguished visiting professor a few times in India at the IIT Institute in Bombay, and also at Bangalore, where there is an excellent institute outside Bangalore of the Indian Institute of Science. He actually was getting several teaching prizes for exceptional teaching, and very important, he also got the so-called Afferson-Schlenk Award of the Deutsche Chemical Society, and the metal for his achievements in the area of lithium chemistry. And for our field, Dietmar is especially important and precious because he initiated a very good program, DFG priority program, on experimental charge density determination as the key to understand chemical interactions. And within this program, really plenty of group, plenty of scientists had a chance to contribute, to develop. So the whole community is very grateful for these activities. So Dietmar is co-author of incredible number of papers, 624, 21 books, 9 review articles, 2 edited books with extremely high Hirsch index 71, and with very broad interest in main group organometallics, organolithium compounds, low valence silicon, S&P centered ligand design, fluorescence chemosensors, and method development in low temperature X-ray diffraction, experimental charge density determination, mass and NMR spectroscopy, and as you can see in the latest volume, which has just appeared in press of international IUCR journal, there is excellent paper on periodic Hirschfeld atom refinement, co-authored by Dietmar. So actually, when let me finish by saying that when we were younger, I was competing with Dietmar in the number of young students whom we were taking to different international conferences. Sometimes Dietmar was better, sometimes me, I can proudly say. So Dietmar, today we'll talk about reactivity and bonding in lithium organics from charge density. Dietmar, the screen is yours.
Krzysztof, thanks a lot for this very warm welcome and for this very, very nice introduction of my person. I must emphasize that I never, ever have beaten the multi-poles on any conferences. There were always more Poles than Germans. So this was very kind of you, but I never made it. All right. So let me start with a talk and just emphasize the importance of lithium chemistry. As you may know, lithium is the lightest element in the periodic table if it comes to metals. So only 3 electrons. However, this metal is, say, undispersible in any industrial process. So as you can see from the first transparency, talking about energy and gas in the first statement, maybe fusion is an alternative to gas and combustion. Fusion, of course, would be enabled by lithium-6 and deuterate, which is the blanket material of this fusion reactor. Hopefully that will work. In any material, lithium is indispensable because it has the option to decrease the thermal expansion coefficient to materials like ceramics and glasses. 1/3 of energy in the world is used by beating friction. So as you can see in these bearings, they wouldn't work without any lubricants. This is lithium stearate, and this is a material which is used from lithium. A bit of history. History was lithium was discovered in the 1817 by Arvidsson Schlenk, working in this in his lab from Jens Jakob Berzelius in Stockholm, and he discovered lithium in a semi-precious stone. That was spodumene, where we have a reasonable amount of lithium then there, and he made that to sulfate and isolated lithium. In nature, there are deposits in Southern America, especially in the deserts there. In the Atacama Desert, we have deposits of lithium, which is reasonably environmentally friendly mined. The mining is just drilling holes in the soil, and then the brain comes up and is pumped up, and that contains a lot of lithium products in there. And then the sun in the desert, from the ponds, from the brain, does it works. It is evaporating the water, and then the lithium products precipitate along their solubility product. And at the very end, we will have lithium carbonate, and this lithium carbonate is the starting material for any lithium-containing product under the sun. So this is principally drugs. So these organic syntheses, the CC bond formation, always relies heavily on at least one lithium organic intermediate just to connect one issue to the other. Well, you could take actually the lithium carbonate directly, because that balances the bipolar disorder, because it mellows the depression and the euphoria, and then you have, say, a reasonable steady state. Maybe this is discovered by the lemonade production in the 30s, when we had this world global depression. Everybody was depressed about losing her or his money, and then they put it into a lemonade, and that was called 7-Up. This is still 7-Up is still there. Of course, this is the mass of lithium, and up, of course, is the alternative to down, and that was appreciated even by the youngest customers in the field. So this is not the cocaine from Coca-Cola, but this is the mild lithium carbonate from 7-Up. Of course, these days, lithium is an eminent important material for electromobility, and in battery materials, the anode material is from lithium. This is not very, very, heavy. The heavy batteries are coming from the cathode material, which is cobalt spinel, and that makes them heavy, but it's not the anode. So we need huge amounts of lithium to work with. I'm talking about organolithium synthesis, and that was lifted off by Wilhelm Schlenk and Johanna Holz when they made methyl lithium for the first time in 1917, when they started from soluble lithium ethylene with dimethyl mercury. This is one of the most toxic metalloorganic you can envisage. So those people were not shy at all. So they reacted the two and then precipitated out lithium, methyl lithium from solution. And in the meantime, they developed the glass apparatus we're using still in metalloorganic chemistry, which is called the Schlenk apparatus. So remember, Schlenk was a chemist, not a glassblower, right? He was a chemist and a glassblower, but not just a glassblower. So that was especially made for this sort of chemistry. So that is already pointing towards the, reactivity of lithium organics. This is a boon and barn of lithium organics. They are very reactive, so they can do anything. However, they are very difficult to handle. So what you see in this video is a crystal coming to the screen and immediately catching fire if it is air exposed. So lithium organics are just only handleable in protecting atmosphere and under cold conditions. So what you can do, as I said, is a lot in reactivity. So you can start with lithium organics right in the middle and then add an aryl or alkyl halide, and then you precipitate out lithium halide to connect a CC bond. And that is in drug design is the almost last step where you can have stereo and regio selectivity. If you want to use the lithium organics as a base, then you deprotonate a starting material. You're losing butane or methane, which is very clean, and then you get a very clean product. You can add lithium organics across a double bond, and you can do that stereo and regio selectively. And you can add that across a carbon-oxygen or a carbon-nitrogen double bond to end up with an amide or an alcoholite. Even material which is say, has the reputation of being very inert, like TMS, you can react with lithium organics and then convert that into a starting material. Well, we're talking at the end of the talk, we're coming to the lithium amides, which are then deprotonated by the lithium organics and then normally form a lithium nitrogen bond. Well, this is not just all of the reactivity, you have to take into account the solvent. It matters a lot in lithium organic chemistry whether you're taking polar or an unpolar solvent. If this is donating, then you have an ether or an amine, and then you have to vary the polarity of the solvent. Even more so, the temperature plays an eminent role. Most of the reactions are done at chilled temperature. At least you need to have at least an ice bath, even better a hard ice or dry ice temperature at -79 degrees. Some of the reactions are done at room temperature, but not at elevated temperatures. Then the donor base is important to deaggregate the lithium organics. If you use a monodentate, bidentate, or tridentate donor base would matter a lot. Or you could create solvent-separated ion pairs where you break the lithium-carbon bond and isolate the lithium in the donor base like a krypton. So that changes reactivity. So the monomers are the most reactive lithium organics, and then climbing up with the dimers, the tetramers, the hexamers, and at the end we have the coordination polymers, which we can have as well. So they're losing reactivity along that line. If we look at the structures of lithium organics, then we have an overarching structural motif in lithium chemistry. That is a triangle from lithium cations bridged by mu3 bridged by a deprotonated or methylated C alpha from any organic residue. This motif, like Lego, can put together in dihedral aggregation to form a tetrahedron or an octahedron. So this is the motif which we have in lithium organic chemistry. So the first who discovered that was Galen Stuckey in 1974 when he determined the structure of cyclohexyl lithium. What you can see is an octahedron of lithium atoms with the 8 faces. 6 of them are bridged by the deprotonated carbon atom, and 2 of them at opposite sides of the octahedron remain unoccupied. This is the principal building block in N-butyl lithium, which is the industrial most interesting starting material, is the same pattern. And then a couple of years later, from Ulrich Siemeling, we had the isopropyl lithium with the same pattern. What you see from the structures is that the lithium C alpha distances are not that much shorter than the C beta distances. Look at this, there is only 2 picometers of a difference, and they are similar in the isopropyl lithium. So the contact to the C beta was envisaged to be a sort of a agnostic interaction from the lithium to the hydrogen atoms of that carbon, but that was cleared later on in 2001 by our dear colleague Wolfgang Scherer. There was no bonding interaction between the lithium and the hydrogens. There is an interaction between the carbon and the lithium. So the carbon, of course, has the most charge density, and that is attractive to the lithium. And the same is valid for the tetrahedra. So the first was Dietrich determined the ethyl lithium. As you can see, all the carbons in the beta positions, they are eclipsed to the tetrahedron. So that is an attractive interaction between the lithium and the carbon. I filed the distance in methyl lithium. This is something awkward because there is no C beta in methyl lithium, but this is, say, the coordination in methyl lithium determined by Erwin Weiss and Cockcroft by powder neutron data. So they located the hydrogen atom positions, and they are staggered to the lithiums and not eclipsed. So they try to avoid the lithiums. And what they do is they aggregate to this tetrahedron. So we have a backside attack from this methanide from the next by tetrahedron and vice versa. So we do that in a strand of molecules, which is then in fact the room diagonal of the methyl lithium structure. If we do that with the 3 other methanides as well, then we build up the elemental cell of methyl lithium, which is a cubic inner-centered cell. And the tetrahedron in the middle is then connected via long-range interactions to all the neighbors. That, of course, is reminiscent to the structure of halide, so rock salt or lithium fluoride. So what we have is a 6-fold coordination of the lithium with the halides. And can we anticipate different bonding from here and the methyl lithium? Methyl lithium is an incredibly insoluble material, so you can hardly solve that in any organic material. And you can have solutions in ether, but in cyclic ethers you can't, because methyl lithium is cleaving those ethers. So it's very difficult to handle that. Is this qualitatively different bonding? And the answer is no, it isn't. If you take the rock salt structure and then take out one elemental cell from there, so forget about the rest, and then take just one cell with 4 metals and 4 halides, which is an AB lattice, of course. And now we connect the lithium atoms, and then we give up the halide metal interactions and connect that to the face of the tetrahedron. Then we have almost the structures of lithium, methyl lithium there. We just need to change the color from the halide to the black of the carbon, and there you go. There you have morphed the methyl lithium structure from the lithium halide. So we can anticipate a sort of, say, continuum between the rock salt structure plus the molecular arrangement in methyl lithium. If this is true, then we need to look at the aggregation and de-aggregation. So the overall formula of lithium organics is RLI. And that, of course, can be 4 or 6. So if N is 4, then we have a tetrahedron, like here, the tertiary butyl lithium structure. So the capped triangles in the tetrahedron, no donor base, no ligands to that. So that, of course, would mean that we have an isolated molecule, not a coordination polymer as in methyl lithium. If we add a donor base like diethyl ether, then we get a dimer. So the lithium is now coordinated, 3 coordinated by 2 diethyl ether molecules and bridging the 2 tertiary butyl groups. But take care, don't handle tertiary butyl lithium in diethyl ether. That tends to explode if you rise the temperature higher than -40. So you need to work at Cardi's temperature, then you can increase the basicity of tertiary butyl lithium by adding diethyl ether. But this is dangerous. So keep your reaction vessel cold at any time. So if you add a donor base, a chelating donor base like sparteine, then my dear colleague Carsten Strohmann isolated this monomer where he had only 1 lithium carbon contact, and this material is, as you can envisage, basic as hell. So this is a really reactive motif in lithium chemistry. So we need to look at the bonding in lithium organics. So as I said, we connected the lithium atoms. Do we really need to connect them? Is this metal-metal bonding, or what keeps the thing together in the inner? So I doubt this is metal-metal bonding. First of all, the distance is fairly long, and we never ever could see a bond path between the lithium atoms and those aggregates. So here is the latest results together with Carsten and his group. We isolated the isopropyl lithium together with a donor base, which is quinacridone. This is the azar bicyclooctane donor base with one nitrogen and then not any further coordination site. So 2 of the lithium sites are coordinated by this donor base, and all the faces of the tetrahedron are kept by the C alpha. So if we look at that in the charge density and multipole, analysis, then we could find all the bond path. So the bond path comes from the carbon to the 3 lithiums, but there is no bond path between the lithium atoms. So that was the first hint that there is no bonding. In fact, in the NMR, you can see the coupling to the carbon and the 3 lithiums in form of a quartet, but you can't see lithium-lithium bonding in the coupling. So you don't have coupling in here. So if this was a hint for bonding, because you need to have a scale-up contribution to bonding for NMR coupling, then yes, the bond path is real, and yes, the absent bond path between the lithiums is real as well. So we could find all the bond critical points, all the ring critical points in yellow, and all the cage critical points in green. So the Poincaré-Hopf equation is satisfied. If you look at the second derivative of the charge density, the Laplacian, then we could see in the non-bonding regions of the carbon, we could see the VSCC, the valence shell charge concentration, which is pointing to the center, almost to the center of the of the triangle, of the lithium triangle. The same is valid for this. This is quite reasonably high, so a good hint for the basicity of the Lewis basicity, actually, of the carbanion. If we if you switch the carbanion from the isopropyl to the tertiary butyl, then we get a dimer. And again, in the dimer, we have a puckered ring. It is arranged in an ecliptic fashion, where the lithiums, of course, have to contribute to the overall crowding, and then it's quite clear that the ring needs to be puckered. In the good old days, there was anticipated that there was some bonding across the 4-membered ring, but there isn't. So trust me, there is no bond path, and the VSCCs look quite similar. So how about the monomer, which was determined in a, I'm reluctant to say in a routine structure determination, so say in a less high resolved structure determination, was determined earlier on by Carsten and Katja Strohfeld when we worked together in Würzburg. That was the structure, and we had the chance to look at it with more sophisticated techniques and better machinery these days. So we found all the bond path as well, and we had a huge lump of density pointing directly to the lithium. And this is, of course, now very nice to compare with the lithium-nitrogen bonds. So, as I said, there is a miracle to the donor bonds, and is the qualitatively different between the carbon and the nitrogen. As you can see, there is atom-like behavior. So red is depletion, blue is accumulation of density. Of course, everybody knows electrons are blue, right? Then we see a round, undisturbed lithium cation depleted by all the electron density, and then the VSCC pointing towards the lithium in the same fashion as the donor base does, as the electronegativity of nitrogen is higher than that of carbon, 2.55 for carbon and 3.04 for nitrogen. It's more contracted for the nitrogen. However, there is hardly any charge, shared between the lithium. It's a very atom-like, say, ionic behavior to both of them. And that, of course, then makes a difference if you add a donor base to any lithium organics. So if we switch to the amides, then the amides are almost as important as the lithium organics because they are powerful branched bases with weak nucleophilicity. So they deprotonate rather than substitute. So the donor base controls the regio and stereo selectivity. Again, we have donor bases, which is then deaggregating the overall lithium amide. This was earlier on discussed by my dear colleague, Reb Mulvey, and the two people I did postdoc with was Paul Schleyer and Ron Snaith. They studied that in detail. So what we have is high solubility of all these, starting materials, and then they are very important deprotonation reactions in synthetic protocols. That is what they call LDA and LIHMDS. So look at this in, orbital control for runaways. So if we had an tri-coordinate amine, then the amine would have a lone pair at the top of the pyramidal environment of the nitrogen, which is donating towards the lithium. That would be a donor bond. This was called earlier on by Arne Haaland and others a donor bond. If we had the nitrogen deprotonated and a negative charge on there, then we could have a sp2 hybridized amide, which has one electron in an sp2 hybrid orbital, and that was donated in a covalent fashion to the lithium. And then the lone pair resides in a pi orbital at nitrogen. On the other hand, some people said, well, we have sp3 amide bonding. This is the reason why we have stereo control. Then the concept is we have two lone pairs at an sp3 hybridized amide, and with one of them, the lithium is interacting, and the other one does the stereo control. So this is hard to believe, as we cannot isolate any amine because they, of course, swinging through, and it's very, very hard to believe that would happen to lithium chemistry. However, that was a concept when we started to look at those materials. So what we need to do is we need to have an experiment where we have all these scenarios in one molecule. If we just switch the molecule for one to the other to the next one, then the synthetic chemists escape behind the back door and then say, look, you changed the system. This is not valid. You have to look at the same molecule. And this is the molecule we looked at. We have a pyrrole ring. The pyrrole ring is deprotonated. So this is the amide. And then we have donating side arm with a dimethyl amine methylene side arms on here. And that whole business is a dimer. So we have two lithiums and then coordinated to two donor centers and two amides. And as you can see, if we look at these molecules in the plane of the pyrrole ring, it's quite a different environment for N4, this one up here, and N1, this one down here. So it is already envisaged from the geometry that we have a amalgamation of all the bonding types in here, and that makes it particularly challenging and particularly interesting to study this molecule. Well, this is the sort of data for the crystallographers we're looking at. We need to have high resolution data, almost 110 degrees into theta. We need a hell of a lot of reflections. We need to have independent reflections. We need to have good R values for the comparison of the reflections. We need to have completeness. So there is no point in losing a cone of angles. If we refine the molecule with the independent atom model approach, there are reasonably good values. The WR2 is pretty high because we have so many data. It turns better if we multipole refine the molecule, then the R value gets even better. And which is most important is the residual density map got even more flat and featureless. So this is the again the amount of data we're talking of. This is completeness, 100% up to the resolution of 0.45. Then we have multiplicity. I hate the expression of redundancy. Redundancy is no good. So what we need is multiplicity, right? We need to have multiplicity, so every event needs to be observed as frequent as possible. And there is no point in driving about your detector in an area where nothing happens, right? Dark screen is done in calibration, but not in data collection. So up to here, we have 9 to 8 times background, and this is what I call a reflection. There is reflection down out there. And the RSIM is very good at 11% to that high resolution. So this is fairly good data. From a home machine, by the way, not a synchrotron. Okay, this is what we look at the residual density when we multipole refine the molecule, and there is clearly the sign of the shashlik-like behavior. So depletion in red and accumulation in green, that behaves like a shashlik, like a barbecue. So we have the meat and the paprika and the meat and the paprika, and that is a clear sign for anharmonicity. This was discovered by my dear fellow Regine Herbst-Irmer, and she had a method to cure for that. And then we cured the data for anharmonicity and got even a nicer result. So as you can see, C6 is now cured from that, and so is C19. With that data, we did the multipole refinement and the topological analysis. So we could find all the bond critical points, and we looked at the VSCCs again. Well, to our surprise, we could only find 3 VSCCs at every nitrogen, at the amide nitrogens. We anticipated, of course, 4 of them because the bonding to the lithium was anticipated to come up with a VSCC, but they didn't. So that, of course, would mean that we have different bonding in here. So if we look at N1, then lithium-1 is more or less in the plane of the ring. That would mean this VSCC is very close to the lithium and almost on the bond path. And that would mean that we had a hybridization which could be rationalized as a more or less covalent orbital controlled bonding to that lithium. So this would be then lithium-1 to lithium 1 to N1. If we look at N4, then the 2 lithiums are well above and underneath the plane of the 5-membered ring. And that would mean we have a different scenario. Is this the scenario we're looking for the stereoselectivity, so for the sp3 hybridization of the nitrogens? No, because we are lacking the 2 VSCCs towards the lithium. There is only the 1 over here. So if we look at that in terms of rabbit ears, that would mean we have sp2 hybridized nitrogens, and the 1 is standing orthogonal on the lithium-lithium vector, and that would mean that these VSCC points to both lithiums and addressing them, the 2 of them. So that, of course, is then the environment for this one. So that would mean this is parallel to the 4-membered ring, and this one is more or less orthogonal to the ring. And that would mean that we have to address both bonding scenarios. And then we looked at the database for all the lithium amides and all the lithium amide bonds in there, and which would, of course, then mean that the relation between D3, which is the distance of 1 lithium from the plane of 1 amide, and the distance of the other one, that needs to be, say, maximum. If this is a minimum, then we have the scenario where both of them are in an arrangement where they cut the lithium nitrogen lithium angle in half, but they don't. They are in a stepwise arrangement, and that is true for 118 hits in the database, and that disagrees for 73. And I must say, at least 50% of those 37 disagrees. They shouldn't be in the database anyway, right? They are not of very high quality. So sorry, I don't mention names. So what we look at in the residual density and the Laplacian, the deformation density, we have to separate N1, where we have the lone pair, the residual density, more counted towards lithium-1 as in the lithium-4. This is almost on the bisection, ideally on the bisection, and this is pointing towards lithium. These changes, of course, the differences are minute, however, they are there. So this is minute chemistry anyway. But amazingly, the donor bond from the lithium, from the side arms, for all four of them, they don't differentiate that much from the amide bonds. So they are a bit more structured, a bit more directed towards lithium, not that diffuse. However, they have to share two lithiums, and that one is only addressing one lithium. That contracts the density, of course. But among brothers, they are all the same, right? And this is, of course, then pointing the way to the importance of donor bases to lithium organics. So if we look to theory, of course, theory needs to be looked at to come up with some energies. Then this step arrangement of the pyrrole rings in this molecule, where we have the alignment parallel to the lines, is 4.1 kilocalories more stable than the bisection mode. And it's a good hint. 4 kilocalories means a lot in this sort of chemistry. So what is the contribution of the various energies? And there the Tonner-Franken approach to the energy decomposition helps a lot, where we can calculate the contributions to the overall interaction energies. So electrostatics is overwhelmingly contribution to the lithium organic, to the lithium amide bonding, so 500 kilojoule per mole. Second is orbital control. So this is not that much orbital control in there. However, 25%, this is a quarter. This was, of course, going up and down in ways during lithium organic chemistry. So at the moment, we are a quarter of the energy comes from orbital control. So this is where the stereo information sits. Dispersion is only 2.6%. So the take-home message is in nitrogen in lithium amide chemistry shows no stereochemically active lone pair character. So the stereo control wouldn't come from the lone pair, but it comes, of course, from orbital control. The database structure, they suit the idea of an sp2 hybridized nitrogen in all amides, not only in aromatic amides. The lithium nitrogen bonding is 27% ionic and 25% covalent. This is a lot, and that, of course, would mean that the donor base is on par with the covalent bond and the ionic contribution. So all of them, of course, would make the story for reactivity. So talking about reactivity, that would mean that you have to ensure that your molecule from the solid state is very much the same as it is in solution. That most chemists work in solution. Industry works in solution, not in solid state, only in solid state catalysis, but this is a different matter. So if we talk about polythiophene. Polythiophene is an incredibly important material in OLED systems, where we have organometallic organic light emission diodes, where we can have foils for televisions and stuff like that. If we do that with lithium reactivity, then of course we have to metallate the the thiophene first, and that can be done either in the 2 position or in the 3 position, in the 2 position or in the 3 position, or in either side. So it matters a lot what is in the pot if you want to make a material which is reliable. So in a collaboration with Anne-Christine, when she was still in my group, we had the 4 structures determined. So there again is the tetrahedron, there is the dimer, and there is the monomer. So we learned from Carsten Strohmann's chemistry and added a tridentate donor base, and then we had a monomer. But how the heck can you tell what is in the pot if you don't crystallize them all? So what Anne-Christine did, she made a dream coming through. My dream from early work with Waldi Bauer, when he developed the 1H7 or 6 HOSI experiment, was to quantify the cross peak in the experiment to the distances. With those structures in hand, of course, and with the sophisticated NMR experiments from Anne-Christine, we could do that, and we now could scale the FID to the distance, and then from there we could clearly identify what was in the solution. So there's always the one unknown feature in solution, and this is this guy. We couldn't really figure out what is this in the solution with diglime. With a diglime donor, you create a lithiate. So what we do is we surround one of the lithiums with 2 diglime molecules, which is the cation. And the anion is made from 3 anions only coordinated to 2 cations. And then one of the diglime is bridging the 2 lithiums. And that, of course, wasn't on the card at all. So we didn't envisage that molecule to be around. But it is, of course. And that is the same experiment we did. We run the NMR from the cross peaks from the HOSI experiment, from the build-up curve, from the AXI experiment. We could in fact identify that the molecule in the solid state is 1-to-1 present with another dimer. So one of the side arms coming loose, making the bridge to not coordinating the lithiums. And then we have the ordinary dimer and the lithiate 1-to-1 in the solution. And that, of course, would matter in any industrial process. You need to know what is in your pot. So this is the take-home message, the overall take-home message from this talk. So ensure your solid-state molecule is present in solution. That helps a lot. So if you could say pin down your molecule in solution and it is there, then you're safe. You need to run a solid-state MRS NMR to find out, to bridge the sticks between solid-state and solution. You need to ensure that your single crystal material is not only the least soluble material in the pot, right? That crystallizes out first. It needs to be still to be there when you run your reaction. So monitor your solution in the NMR and vary the temperature in the NMR. That helps a lot. Ensure that your material is reacting, which is, of course, say redundant to say. However, sometimes it reacts with join grease, or it reacts with whatever is in the pot with a solvent and not with your reactant. And this can be figured by residual dipolar coupling or residual quadrupolar coupling NMR in solution, where you can take advantage of diffusion. So this is it. I thank you for listening. I thank all the co-workers for helping me. I had so many, say, capable people in the group over the years. I thank them all. I thank all the collaborators in Göttingen. So Ricardo Mata and Jörg Behler helped a lot with theory. I thank George Sheldrick helping with programs, theoreticians in Germany, all over the world, experimentalists giving their nicest molecules to me to let me study them. And I thank them all, and I thank you for listening. And questions are welcome. Thank you.
Thank you very much, Dietmar, for excellent lecture, which is now open for questions and comments. Please put down your comments on chat, and they probably will soon appear. Yes, first people are writing. Before we get the first one, would you agree that there is a certain degree of similarity between hydrogen bonding and, some people say, lithium bonding? Do you see this kind of similarity, or rather not?
There is the similarity, of course. Yes, it's the charge. So for any hydrogen bond, you need to have a polar environment. So you need to have the positively charged proton and the negatively charged acceptor. So the donor and the acceptor would be the lithium would be the acceptor, and the hydrogen would be the donor. However, that wouldn't work with lithium, because you have the, say, positively charged, say, CH or OH from the donor in a hydrogen bond. So what you need to have is a hydride. So once you have a hydride, then you're fine. So then the lithium hydride would be, say, an inverted polar hydrogen bond, to put it that way.
How about electron density? How about electron density? Lithium has only, lithium cation actually has only one electron more.
That's right.
How it is
positive?
How it is visible on the density maps when you compare it to hydrogens from X-ray diffraction?
Well, it has an inner core, and it is depleted. So,
but it's much easier to see it than hydrogen, right?
It's much easier to see. Yeah. It is, say, it say takes advantage from, as you can see, the lithium, the inner core. You can see an inner core, so there are 2 electrons. Rather than for the hydrogen, you don't have any electrons. They are all sitting in the bond to the carbon, or in the bond to the nitrogen. But for the lithium, you have the 2 inner electrons, the s electrons, where you have the, say, not say, there is something left.
And probably it also the thermal motion of lithium atoms is much smaller than for hydrogen, right?
It's much say lower than the dangling hydrogens. That's right. Yeah.
So we have a question from Martin Lutz. Dietmar, what scattering factors are you using for lithium?
Yeah, Martin, we can have either that one of lithium plus or of lithium. That, to be honest and frankly spoken, wouldn't matter that much. So the scattering factors we normally have for lithium plus, because this is closer to reality.
And how about the multiple refinement then? Are you able to refine any valence electrons on lithium, or?
Yeah, that is always possible. We have problems with transition metals, but not with lithium. That is
so what kind of charges are you getting for this lithium cations?
For the approaches, they vary, of course. Beta charges are plus 0.98, 0.8, 0. Whatever. Other charges go down to plus 0.5. So the beta charges are very, very positive.
How about the valence electrons populations from multiple model? You remember?
No.
Pival. Okay. So we have another question from Sunak Sarkar. Is it possible to control formation of a stereochemically active lone pairs by tuning lithium-nitrogen bonding?
Well, never say no, but no-ish. Well, to my firm belief, it is not possible to have stereo control by tuning that bond. I mean, what you can earn is plus or minus 5% to covalency or ionicity. So it is mainly ionic. I think whatever you do, you have to come up with say, stereochemically auxiliaries like spartiene, like controlled and fixed stereo centers. I think just by tuning the lithium nitrogen bond, that wouldn't help. So stereochemistry, no. Reactivity, yes, a lot. Is this so?
Yeah.
It's okay.
We'll see soon. Dietmar, this Shashwick-like, say, arrangement of residual density, we sometimes see that we are getting this kind of effect when weak reflections are removed from the refinement. When all reflections are, say, considered, then this effect sometimes is disappearing. I think it's important to check this during the refinement.
Yeah.
Because in some cases, this Shashwick-like arrangement could be induced by removal of reflections.
Yeah, you're right. We saw the same. This is of course very heavily dependent on the data set you have. So a couple of reflections make a hell of a difference. So we always try to work with all of the reflections because they want to tell you something. So I forgive me, Martin, forgive me, Ton. I hate squeeze. To squeeze out something from a structure, if it is data or if it is information on solvent or something like that, is not really cricket. We have to work with the experiment. So the answer could be ignore those reflections or say correct the data. As far as I'm concerned, and Regina hopefully will join me in, is I quite like the idea to say correct the data, because corrections are very familiar to crystallographers. We have to correct for absorption, we have to correct for extinction, we have to correct for so many effects. Why not correcting for, say, anomicity?
We have a question from Yasir Balmohammadi.
All right.
Did you?
I can read it, Paulina.
Yes, yeah, but I will read it for those who you have no access to that. Did you try to build a cluster of molecules? Do you think it makes any difference?
Yes, we did. For instance, we used deliberately the wrong donor base for methyl lithium. What is the wrong donor base? The right donor base would be a donor base where you have the bite to each lithium. If this bite angle is artificially too narrow, then of course it swings around and connects another lithium. And this way we build a channel methyl lithium with a donor base, which is a huge cluster, which is a channel. Unfortunately, this channel is not racemic. Is not enantiomerically pure. It is racemic. Otherwise, it would be a nice idea to introduce stereoselectivity by this, well, arrangement in channels. That unfortunately didn't work. So we still have a center of inversion. Damned.
Thank you very much. Are there any more questions or comments? As apparently there are no more questions nor comments. Let us thank Dietmar again for his excellent and for interesting discussion. Thank you very much, Dietmar.